Hello, my name is Marissa Hunter. I'm here presenting with Jennifer Nishimura on our computer architecture project showing our use of logic.ly and the different circuits we have built with it. I'm now going to share my screen. I'm going to share everything. Nice. Hopefully you can all see that. This is a 16-bit ALU. It is composed of 16 1-bit ALUs, as I will show here. Let me just go to it. Okay, yes, this is my 1-bit ALU slice. It is composed of 3 units: the decoder, the logic unit, and the full bit adder. The decoder is shown here. This is the makeup of that. The logical unit is composed of the circuit, and lastly, the full bit adder is looking like this. So there's a sum and a cout, and all in all, this makes the 16-bit ALU. Now we had some cases that we were supposed to test. The first case was, Jennifer, are you able to see my cases right now, or do I need to share that individually?
I can see your cases.
Cool. All right. So our first case is negative 30,584 and negative 481 with this as the input, 110000. Those cases are shown how to do them down here. And I've already set up the first case. So A is the negative 30,000 and the B is the negative 4,000 with these bits here. And the output is a 1 in this spot and a 1 in the fourth to last spot. And that is what is expected in this right here. All right, now we're going to try the next case. It is the same input here, but instead of the negative 30,000 and negative 4,000, I'm going to do positive 4,000 and positive 30,000 plus change on each of those. Okay, so the 30,000 one will go on the B, so it's 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, and then we'll look back what our A is supposed to be. Our A is, so the ones in the 8 middle slots. 1, 2, 3, 4. 8 middle slots. Oops. Okay, output looks to be like this. And now let's look at our expected output. That is exactly what we find, that the ones are in these positions, as you can clearly see here. All right, let's move on to our next case. Instead of 1, 0, 1, 1, 0, 0, 0, 0, we're going to put a 1 in the last zeros position, and we're going to do the exact same case as number 1 with negative 30,000 and negative 4,000 plus change. So let's change that at the beginning. This, and then we're going to go 1, 0, 0, 0, 1, 0, 0, 0. Sorry, it takes a while to do this manually. 1. All right, now I need to remember how to do the negative 4,000. Yeah, the ones on the outside. 2, 3, 4. 1, 2, 3, 1, 2, 3, and then those 4. Right, make sure I have all the right inputs. All right, we're left with 5 ones, 3 zeros, and it keeps going. You can see what it says. Our expected output: 5 ones, 3 zeros, a 1, 3 zeros, 4 ones. Let's see. 1. Yep, that's exactly the output we have. All right, let's move on to the next case. The next case is again the 4,000 and the 30,000 plus change, but this time the 1 is in this output. This is, as you can see here, an OR gate when the last ones were AND gates. So I'm going to do that 4,000 as the A, which is the ones in the middle, and then the 30,000, which is that. Okay, I think I can remember that. 1, 2, 3, 4. and then 4 zeros at the end, perfect. And then we're gonna go 0, 1, 1, 1, 0, 1, 1, 1. Sorry, it's kind of hard to see because it's so zoomed out, but it is a large circuit. And we have these outputs, correct? Yep. All right, so what we want is a 0 in the first position and a 0 in the fourth to last position. Let's make sure that's what we expected. So this is case number 4. So we have a 1 in the first position and then 1 in the negative fourth. In the fourth to the right. Yeah, that position. So we got exactly what was expected. All right, now we're going to move on to the not be cases where we have a 1 in the second to last position instead of the last position. We again are going to go with our negative 30 and our negative 4,000 case, which is these two cases here. So our negative 30 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so that's our negative 30,000. And then for our negative 4,000, we are going to do 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1. And instead of this one, we are going to move it so that the input is the second to last one, and that is our F0 input instead of our F1 output. I know those labels are hard to read, but that's what it says. You can check our PDF for the zoomed in version. So what we're getting is the middle 8 bits are 1s, and that's exactly what we expected. The middle 8 bits are 1s, while the other ones are 0s. All right, now we're going to do another not be case. So the same lineup for this, but we're going to use the 4,000 and the 30,000. So the 4,000 is the middle. Okay. 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. Get rid of this. 1, 0, 0, 0, 0. And then it's 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, that expects to have a 1 in the first bit location of every 4 bits. Let's make sure that's what we wanted. Yep, yeah, the first bit is a 1, while the next 3 are 0s, repeating that over and over. That's exactly what we wanted. Now we're going to try to do our add case, which is both the last 2 digits here are 1s. So that's with our negative 30,000 and our negative 4,000. So we can set that up. 1, 2, 3, 1, 0, 0, 0. Get rid of that. 1, 0, 0, 0, and then the negative 4,000 is the ones on the outside. 1, 1, 2, 1, 0, 0, 0, 0, 0, 0, 0. So all 8 bits in the middle are 0s, while the outside ones. So we turn that on. So now we have 1, 1, 0, 0, 1, 1, which is our add function. So what we should see is the same as this. Let me make sure I did the right. Oh, I didn't see. This is actually supposed to be a positive 4,000. So let me switch. All of these should be switched since negative 4,000 and 4,000 are just the inverse of each other. So now all the middle bits are going to be on, the middle 8 bits, and then the outside 8 bits are going to be off, 4 on each side. All right, let's see if that gets us the output, because the last one is incorrect. Okay, so it goes 1, 0, 0, 1, which you see here, 1, 0, 0, 1, 1, 0, 0, 0, so 5 zeros in a row here, 4 1s, and then 3 zeros. So we got 4 1s, 3 zeros. I think I said that wrong. Oh yeah, sorry, only 4. So it goes 1, 0, 0, 1, 1, 0, 0, 0, which we have here, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, which is not what I said, but that is what's here. So that is the exact output we were hoping for. Let's try our last case. This involves two new numbers, 256 and 1024. 256 only has a 1 in the 8th place. So I'm going to turn off all of the digits on both sides, just because we're not going to need any of these switches anymore, except for 1 on the A section and 1 on the B section. All right, we're going to count 8. 1, 2, 3, 4, 5, 6, 7, 8. And then on the 1024, we're going to want it in the 6th position. 1, 2, 3, 4, 5, 6. All right, that turns on the 1, 2, 3, 4, 5, 6th and 8th bits. Let's see. This is our 8th case. It turns on our 1, 2, 3, 4, 5, 6th and 8 bits. So this shows that all of the functions, the add function, the OR function, the not B, and the add function, when working with both positive and negative numbers, this case right here added a positive and negative number and got a negative number. So it shows that it can do signed mathematics. And so this shows that our ALU 16-bit ALU circuit works as it should. Stop sharing. And now Jennifer will show you our next circuit.
Okay, so I'm going to be demonstrating the state machine. I'm going to go ahead and Marissa, I can't share my screen because it says the host disabled screen sharing.
Okay, let me turn that on. There you go. Sorry, it took me a second to find that feature. There you go.
Okay. Share my screen. There we go. As you can see here, the light flashes between red, green, and yellow when the police override is off, and then when I turn the police override on, it will turn red on and off over and over again. So that is the demonstration of the state machine circuit. I'm going to turn it back over to Marissa.
Okay, I will now share my screen to show our last circuit. Let me just pull it up and share my screen. Okay, so I'll zoom out a bit so you can see the entire circuit. There we go. So this is our counter. It counts up and down depending on what this D switch does. When it's off, it counts backwards, and when it's on, it counts forwards. So to get this running, we have to load the preset and the clear. So now you can see that it is counting down every second. You can see that this, well, let me do that. It's not showing it now, but every second the clock cycle is flashing, which causes this to count down. So we're at 5, 4. All right, now I'm going to switch it and it's going to start counting up. 4, 5, 6, and it goes all the way up to F, and then back to 0. If I switch it again, it'll start counting down. I'll show you how it counts down from 0 to F, and then we'll move on with this example. 4, 3. All right, and it goes to F next. This is in hexadecimal, which is why it goes into F, E, D, and so on. And I will stop sharing this now. All right, this demonstrates the 3 circuits we created in this project. This was a computer architecture homework assignment, and those were the 3 circuits we made. Thank you.